Welcome to our lecture on time series in machine learning. My name is Dr. Andrey Holz, and I will guide you through this topic today. Time series analysis is a critical skill for solving problems where data is collected over time. By the end of this lecture, you will understand the foundations, explore advanced techniques, and learn how to apply them effectively. Time series data is everywhere. Examples include stock prices, weather data, website traffic, and even heart rate measurements. Our goal is to uncover the patterns hidden in this data and use them to predict future values. Let us get started. So, agenda for today. We'll start with the basics, what time series data is and why it is different from other types of data. Then we'll dive into the mathematical background where you will learn about stationarity, autocorrelation, and other key concepts. Next, we will explore classical models like ARIMA, machine learning methods like random forest and prophet, and hybrid models that combine both approaches. And finally, we will discuss practical tips such as preparing data and evaluating models before concluding with the best practices and key takeaways. This structure will help you build a step-by-step understanding from fundamentals to advanced techniques. And time series analysis is one of the most applied areas in machine learning. It is used in industries like finance, healthcare, manufacturing, and marketing. For example, predicting sales helps businesses plan inventory. Detecting anomalies in system logs can prevent server failures. In time series, the main challenge is accounting for the fact that data points are not independent. Instead, they are related through time. Models must understand these relationships to make accurate forecasts. A time series is a set of data points collected in chronological order. Think of daily temperatures over a month or hourly website visits. What makes time series unique is the order of the data. It matters. Unlike other data types, you cannot shuffle time series data without losing its meaning. For example, if you analyze sales data, today's sales may depend on yesterday's promotions or seasonal patterns like holidays. Time series can be broken into four main components. Trend, the overall direction of the data, whether it's increasing, decreasing, or stable over time. That's the second from the top here, the green one. Seasonality, it's irregular, repeating patterns such as higher sales every December. So, for instance, they are here like the third one from the top, seasonality. And irregularity, or random noise, or residuals, is just fluctuations that cannot be predicted. And understanding these components helps us select the right model and preprocessing techniques. For example, trends and seasonality can be modeled explicitly, while irregularity is treated as a residual error. By the way, sometimes is the cyclicality involved. It's a long-term pattern not tied to a fixed calendar like economic booms and recessions. So if you can also include this in your analysis. And this makes this time series unique, unlike regression. And yeah, you can see this is the actual decomposition of the top graph, and the top graph is the Bitcoin price actually. So let us get moving. And what is the trend like mathematically? Well, we can calculate it by moving average or by polynomial fitting. Basically, we use smoothing techniques to identify this trend. Seasonality is extracted by observing regular patterns, often using decomposition techniques like STL. Again, you can just use the observed data and subtract trend from this data, and this is like one of the ways to calculate seasonality, because now you do not have trend, but you can try to see what is going on. As for the cyclicity, unlike seasonality, has no fixed period and is often explored through spectral analysis. And finally, irregularity or noise or residuals, it's just random variations, and it what remains after accounting for all other components. These calculations helps us understand and model the data more effectively. As you can see, you can have your observed data and subtract trend and seasonality from the observed data, and now you will have the noise. You might have an idea, well, let us use regression models since they predict the value, not the class, and predict time series. The main issue is that regression assumes all data points are independent. However, in time series, data points are often correlated. For example, if it's raining today, it is likely to rain tomorrow. A regression model wouldn't account for this relationship, leading to inaccurate predictions. Time series models like ARIMA or Prophet are specifically designed to handle temporal dependencies. Regression models struggle with time series for several reasons. They ignore autocorrelation, the influence of past values on current ones. They cannot model trend or seasonality without extensive manual feature engineering. They assume data points are independent, which is not true for time series. For example, predicting sales using regression would require you to manually create lag features and seasonal indicators, which can be tedious and could lead to errors. Mathematical foundations are critical for understanding time series. And one key concept is stationarity, which means the statistical properties of the data, like mean and variance, remain constant over time. Most time series models require stationarity because it ensures that data's behavior does not change unpredictably. You can take a look at this image. So how stationary time series on the top differs from the non-stationary time series. And I would say this is pretty interesting. You can see that the stationary time series are inside the boundaries, while non-stationary time series, they change their behavior. They either grow or there is like a standard deviation that is changing. To check stationarity, we use tests like ADF or augmented Dickey-Fuller test. Tests if data has a unique root indicating non-stationarity, and KPSS tests for stationarity around a trend. If the data is non-stationary, techniques like differentiating or detrending are applied. So what is stationarity from the mathematical point of view? Stationarity can be weak and strict. For weak stationarity, only the first two moments like mean and variance are constant, and autocovariance depends only on the lag between observations, not on the actual time. If we are talking about strict stationarity, then all statistical properties like mean, variance, and higher moments are constant over time, and it implies that the joint distribution of any collection of time points is invariant to shifts in time. So this is indeed really a strict condition. In practice, most of the time series are weak stationary. What about testing time series? Well, as I mentioned, there are two main tests. There are a lot of others, and we can use ADF test, and the null hypothesis there is the time series has a unique root. It is non-stationary, and alternative hypothesis is the time series is stationary. So how to interpret? A low p-value leads to rejection of the null hypothesis, indicating stationarity. As for the KPSS, so the null hypothesis is the time series is stationary, and alternative hypothesis is the time series is non-stationary. It's like the opposite to the ADF test. And interpretation of this hypothesis, so a low p-value leads to rejection of null hypothesis, indicating non-stationarity. And what about testing for stationarity? Well, there are a lot of tests and variations of tests. We'll take a look at two: the augmented Dickey-Fuller test, or ADF, and the null hypothesis here is the time series has a unit root non-stationarity, and alternative hypothesis is the time series is stationary. So how to interpret it? A low p-value of this test leads to rejection of the null hypothesis, indicating stationarity. And KPSS test as null hypothesis here is the time series is stationary, and alternative is time series is a non-stationary. How to interpret it? A low p-value leads to rejection of the null hypothesis, indicating non-stationarity. So this alternative version, or the opposite version of the conditions of the first test. But let us move on. And what about the autocorrelation and partial autocorrelation? The autocorrelation function shows how strongly the data is correlated with its past values at different lags. For example, if sales are strongly correlated with the previous week's sales, and this will appear in the ACF plot, or the autocorrelation function plot. The partial autocorrelation function, or PACF, isolates the direct effect of past values, removing indirect effects. And those plots are used to determine the order of the autoregressive and moving average components in models like ARIMA. The partial autocorrelation function quantifies the correlation between a time series and its lag values after removing the effects of intermediate lags. It isolates the direct effect of a lag on the current time step. And what about the practical implications? So those plots are used in the stock prices to determine short-term dependencies and moving average patterns in financial data. Weather forecasting to identify lagged relationships between temperature values. And energy consumption, of course, to analyze autoregressive patterns in electricity demand. And this is how they look like, those plots of the original time series. And let us discuss those graphs and their essential tools for time series analysis. So ACF plot on the left measures how strongly time series is correlated with its past values or lags, and each vertical bar represents the correlation at a specific lag. For example, the first bar corresponds to how today's value relates to yesterday's, while the second bar shows the relationship with the value 2 days ago, and so on. The blue shaded area represents the confidence interval. Bars outside this area indicate statistically significant correlations, while bars within it are considered random noise. And of course, at lag 0, the correlation is always 1, because time series compared with itself, so it's mathematically. A sharp drop after the first lag suggests a moving average process. A gradual decline or decay indicates an autoregressive process. What about the right panel, this one, the PACF plot? It measures the direct relationship between the time series and its lagged values, excluding the effects of intermediate lags. For example, at lag 3, the PACF removes the influence of lag 1 and lag 2, showing only the pure correlation at lag 3. And similar to ACF, bars outside the blue shaded region are significant. A sharp cutoff after a certain lag suggests an autoregressive process. For instance, if only the first lag is significant, it indicates the autoregressive 1 process. How to analyze those plots? In the ACF plot, we see a significant bar at lag 1, followed by a sharp cutoff. We're talking about the left one. This suggests a moving average process, MA1. In the PACF plot, we see a significant bar at lag 1 and no significant bars afterwards, which indicates an autoregressive process, likely AR1. And from these plots, the time series appears to follow the specific patterns. We'll discuss it during the practical session. So one AR term in a ARIMA model no differencing, and one MA term. And this model captures both the autoregressive and moving average components identified in the graphs. Let us have a coding session where we'll take a look at the time series decomposition and analysis. Hello, this notebook demonstrates advanced techniques for time series decomposition and diagnosis. It focuses on separating time series into trend, seasonality, and residuals using custom calculations and the STL decomposition method. Additionally, it includes diagnosis to analyze stationarity and suggests ARIMA parameters based on dataset properties. Let's start with the dataset and decomposition. So the first approach is to calculate all manually, and to calculate the trend or a moving average, we need to apply rolling window with the seasonal period of 12 months, and this is how we calculate the trend. This smoothes the data to reveal long-term patterns. As for the seasonality, after we have trend, seasonality is calculated by averaging detrended values for each month. For example, the average deviation in January helps identify the seasonal index for January. And these seasonal indices are normalized to ensure they sum to zero, highlighting cyclical fluctuations. This is exactly what we do here, like with seasonal indices. Then we need to map the indices to the dataset, calculate residuals. So now we're just having the observed data and we're subtracting trend and seasonal components. And yeah, then we'll plot it. And yeah, basically, let's take a look at what we have here. Just wait a little bit. Yep, the original time series, the trend component. So the trend is rising. So yeah, more and more people are traveling. The seasonal component, we can see here that there is a pattern and like, or there is a seasonality here. And the residuals that we manually calculated are pretty interesting, I would say. What next is we can calculate the same thing but with the stat models decomposition. So let us take a look, and we will use this pre-made function that calculates everything. Again, original time series, trend component. Seasonal component is a bit different since we're using another tool, and the residual component. What if we have like the seasonal of 12, not 13? Just let's take a look. So what happens? Again, seasonal must be odd positive integer. Okay, 11. Yep, the residuals seem to be bit different. But yeah, let's return to be 13 since that's the standard number for the yearly seasonality. And STL decomposition or seasonal trend decomposition using LOES is a more sophisticated method. It represents a time series into trend, seasonality, and residuals. I showed you how it works, and seasonality captures like repeating patterns, and residuals represent the noise or variations explained, not explained by trend seasonality. Let us have some diagnosis. So what we do here, we apply several tests like a Dickey-Fuller test, and we apply KSSP test for stationarity. Then we'll analyze the plots of ACF and PACF to calculate some insights for the parameters of the ARIMA models. Yeah, and let's take a look how it works. So yeah, Dickey-Fuller test says that the series is likely non-stationary, and this is true since that's it. We have a trend here, upcoming trend. And the second test also says that is likely non-stationary. So differences here suggested orders, and yes, series is non-stationary. Differentiating is required. So this is what is required, and yeah, we can later use it. As for the lags in ACF, like significant lags in the ACF plot suggests the order of MA terms, and significant lags in PACF plot suggests the order of AR terms. And we will use it later. Keep in mind that, well, those things helps us evaluate the model and choose the best parameters for our models. Stationary check summary, orders, and basically, yep, we calculated all that we needed. Let's try apply difference and check what if we apply difference. We can see here like the difference here, but the time series now is likely stationary, so we can operate with this one. So this notebook was to practically demonstrate how to decompose time series into components for better understanding and preprocessing. And diagnostics we also showed to evaluate stationarity and determine the need for transformations. So this notebook equips you with the tools for analyzing and understanding time series. Decomposition methods reveal the structure of the data, while diagnosis ensures appropriate model selection. Feel free to experiment with the data sets and parameters to deepen your understanding and knowledge. And thank you. Welcome back, and let us continue. Now, let us talk about how we actually model time series. So, what should we do and how to approach them? And we already mentioned ARIMA model, so let's take a look what it actually is. And ARIMA is the autoregressive and integrated and moving average, so that's like the letters in the name. It models the relationships between three main components: the autoregressive component, the integrated component, and the moving average component. Mathematically, they are described in the slide, and as for the parameters, we have the P, D, and Q. P is the order of the autoregressive part and determined using the PACF plot, as we discussed, and D is the degrees of differencing. It determined by examining the trend and stationarity of the time series, so the time series should be stationary. So if it is not stationary, we try to apply differencing to it. And the Q is the order of the MA, or the moving average part, and it is determined using the ACF plot, where significant lags indicate the MA order. For example, if sales are consistently increasing, ARIMA can identify this trend, remove it, and focus on the residual patterns. SARIMA extends ARIMA by adding seasonal components. This is useful for data with repeating patterns like quarterly sales. It includes parameters for seasonal autoregression, differencing, and moving average, capturing both short-term and seasonal dependencies. And here we have three parameters that are the same as we had in ARIMA and one more. So the parameters we had in the ARIMA is the order of the autoregressive part, or degree of differencing, and order of the moving average part, but now they represent also the seasonality. And the new parameter is the number of time periods in one seasonal cycle. For instance, like 12 months for monthly data with yearly seasonality. And this is how the SARIMA works. You can take a look at the mathematical implementation, and let us have the summary. We won't dive deeper here, since that's an overview of the time series, and we'll need a separate topic specifically for time series to discuss all in details. But as for the summary, so the strengths of the ARIMA and SARIMA models, well, they are well understood and they are interpretable. There are basically coefficients, and we know how the coefficients are calculated. They're effective for linear patterns and stationary data, or if the data can be reduced to stationary by some operations. The assumptions of those models are linearity in data relationships, stationarity after differencing if necessary, and normality in residuals. And what are the limitations? Well, they struggle with non-linear patterns. They require careful parameter tuning, and it is pretty hard for them to handle exogenous variables. It means that the model does not natively include a mechanism to incorporate external factors, variables that are not part of the time series itself, into the calculations. And these external factors are called exogenous variables. They can influence the time series but are not directly derived from it. Just as an example, if you are forecasting monthly sales, price discounts or advertising spend could be exogenous variables because they affect the sales, but they are not part of the historical sales data. And that would be pretty hard for those models to include them. What about the machine learning? Since, like, we already know some machine learning models, can we use them in a way? We can use some models, for example, random forest, and they're flexible enough and handle nonlinear relationships, unlike unlike linear regression. And those models do not require the data to be stationary and can incorporate external features such as weather or holidays into predictions. So you can use them, but you will have to have the feature engineering part done on your side completely, because those models are not specifically designed for time series, they're general models. So, and if we're talking about tree-based models, well, we can use decision trees, random forest, gradient boosting machines, and the features that you will definitely need to incorporate is the lag features, is the rolling statistics like moving averages, moving standard deviations, and so on, and time-based features like day of the week, month, quarterly, holidays, and so on. And the advantages of using those types of models is they can handle nonlinearity and interactions, and they are robust to outliers, unlike ARIMA and SARIMA, and they can provide feature importance insights which might be pretty interesting and crucial sometimes. If we are moving to the models specifically designed for time series, well, the one that is interesting is the Prophet by Facebook or Meta. It is specifically developed for forecasting time series data, and it is designed to handle seasonality, holidays, and trend changes. The key features of this model is the additive model components, trend, seasonality, holidays, and automatic change point detection, and user-friendly with minimal parameter tuning. As for the advantages and use cases, so it handles missing data and outliers well. It is suitable for business forecasting like sales, demand, and so on. And it is scalable and easy to use for non-experts. Let us talk about the features that make Prophet a wonderful and flexible time series forecasting tool. It uses additive model, meaning it breaks down the time series into key components: trend, seasonality, and holiday effect. And the components are modeled separately and then added together to form the final forecast. Mathematically, the model is represented as the equation. One part represents the trend, capturing the overall direction of the data, whether it's increasing, decreasing, or constant. The next one is seasonality, which models repeating patterns like weekly or yearly cycles. And then the next one captures holidays or special events, such as sales spike during Black Friday. And finally, the final term is the random noise or residuals that cannot be explained by other components. And by separating these elements, Prophet allows us to analyze their individual contributions to the time series and understand how the trends, seasonality, and holidays influence the data. One of the Prophet's standout features is the ability to automatically detect change points. Change points are moments where the trend changes direction or slope, such as sudden increase in demand or sharp decline in sales. This feature is particularly useful for data sets with unexpected shifts. Instead of requiring manual intervention to identify those changes, Prophet adapts automatically, making it easier to work with the real-world data that is often unpredictable. And yet, just look at the charts. Top one shows the trend component, captures the overall increase over time. The next one, the second one, is holiday effects, showing how specific dates impact the data. And then the third one represents weekly seasonality, indicating variations across the days of the week. And the last plot is the yearly seasonality, reflecting patterns throughout the year. Prophet's structure and change point detection make it user-friendly and effective, especially for business data. It provides flexibility in handling trends, seasonality, and events, while also being robust to changes in the data. And these features make it an excellent choice for time series forecasting. What about the hybrid models? Hybrid models combine the strengths of ARIMA for capturing linear trends and machine learning for handling non-linear relationships. You can think of it as an ensemble. For example, ARIMA can remove trends, and random forests can model the residuals to improve accuracy. An advantage of those techniques is like enhances predictive performance and reduces risk of overfitting and increases robustness to different data patterns. The tricky part here is you need to carefully design this approach. Otherwise, well, it's pretty hard to make different types of models work on the time series data. Please also keep in mind that you need to validate the time series in a way that differs from the classical machine learning regression. So you'll need to keep in mind that you cannot randomly shuffle the data. And there are also other notable methods. We won't stop here to discuss them since they require a separate session. I'll just briefly mention them. State space models are flexible for representing time series with unobserved components, and they are allowed to break down a time series into parts like trends, seasonality, and noise, while also accounting for latent states that are not directly measurable. One widely used tool is the Kalman filter, which is like the iterative algorithm to estimate these unobserved states efficiently. It is particularly useful in dynamic systems such as tracking moving objects or predicting financial time series in real time. Of course, Gaussian processes can be used here, and the key advantage is their ability to handle uncertainty explicitly, providing not only predictions but also confidence intervals. And this makes them especially useful in areas like geospatial modeling or forecasting, where uncertainty plays a critical role. And of course, transformer-based models are one of the most recent advancements in time series analysis. Originally, they were developed for natural language processing. However, they use attention mechanisms to capture long-range dependencies in the data. And by focusing on the most relevant parts of the time series, transformers models can handle complex patterns and relationships that traditional methods often struggle with, and they are now considered state-of-the-art. And many time series applications, such as demand forecasting and anomaly detection, use transformer-based architectures. So, and the advantages of these methods is like the flexibility. They can model complex patterns and uncertainty estimates, and the performance. Especially transformer-based models have demonstrated state-of-the-art results in tasks requiring high accuracy, particularly for long-term and large-scale forecasting. And those methods gives us tool to solve the complexity of modern time series problems, especially when working with large datasets or in highly dynamic systems. Let us have a demo. We'll take a look at several models on the real dataset. Let us walk through a hands-on example of time series modeling. This notebook demonstrates a complete workflow from data preparation to applying various models like SARIMA, random forest, Prophet, XGBoost, and finally evaluating their performance. Let's break it down step by step. And the first step is installing and importing required libraries. So here we'll need stat models, scikit-learn, like XGBoost and Prophet. Prophet by Facebook or Meta. It specializes in time series forecasting. Once installed, we import the libs for tasks like data handling, pandas, visualization, matplotlib, and statistical analysis, stat models, and machine learning. Let us move on. So I already installed it, so not a big deal. Data preparation. I created everything in a function way. So this is the simplest data preparation. The dataset is actually downloaded from the URL that I provide. Then all the missing values are dropped, since we do not need missing values here. Again, this is for the demo purposes. In the real case scenario, you'll need to impute the missing values based on some logic, but we can plot the original data, and this is data on the airline passengers dataset. Contains mostly passenger numbers. Let us take a look at it. So what is going on? We'll take a look at it later. So basically we have here two differences. Here passengers original data, so nothing special. Common functions we'll need. Yeah, but by the way, differencing. To make time-step series stationary, we apply differencing, and first-order differencing removes threads. Second-order differencing addresses seasonal patterns. And the visualization here will also be provided. So what about the evaluation of the models? To evaluate and plot, and this is critical for our understanding, we'll use RMSE, root mean squared error, MAE, mean absolute error, and MAPE, mean absolute percentage error, to quantify predictions. As for the, and MSE also, as for the visualization, here we also have the QQ plot of the residuals to check, and the histogram of the residuals. Again, Shapiro test for normality also included, and then analytics of the QQ plot just to help you understand what is going on. We can move on to the models actually. So, and the SARIMA model is a classical time series approach that models trends and seasonality. It uses the difference series and seasonal parameters to forecast. We specify the SARIMA configuration as 1, 2, 1 for non-seasonal components, and 0, 1, 1, 12 for seasonal components, meaning that those parameters indicate how we're using the differences, how we're using the autoregression. We're moving to the random forest and let's say tree-based algorithm, and to adapt it for time series we create lag features like lag 1. Again, this is for the demo purposes, and we can create a lot of lag features here. This is just a demonstration. And we're moving to the profit model, and the profit requires the data to have timestamps and a variable, ds for date and y for values, and we prepare this data. Then it will automatically handle change points, provides interpretable plots and components like trend and seasonality, and the components are visualized to understand the underlying patterns. Let's move to the XGBoost. XGBoost is designed in a way similar to the random forest actually. And here we have the main flow. Let's take a look at it. So we have original data. Obviously there is a trend, and the number of passengers is increasing year by year here. As for the differences of the ACF and PACF, so we can see here that while there is high correlation between the 12 and the lag at 12, meaning that 12 and 24, meaning that the yearly seasonality still exists. Let's run our first model, SARIMA, seasonal ARIMA. We can see here that the QQ plot here shows almost good picture, so they aligned to theoretical quantiles, and the overall prediction is not that bad. It resembles the pattern actually, and the MAPE on the holdout dataset is 4%, which is pretty good, and all other metrics are again nice. So the residuals here not seem to blast, and histogram is around 0. We can also have this table, take a look with all the statistics. But let us move on. Histogram of the residuals. So what residual analysis shows us? Residuals are likely normally distributed according to Shapiro test. And QQ-plot says that our residuals align closely and they are likely to be normally distributed. So all in all, we're pretty good with this model. What about the random forest? Let's take a look. It behaves worse, but again, keep in mind we're using only one leg feature here. So it's random forest with one feature. It's maybe like 12%. Let's move to the analysis. Well, analysis of residuals, again, pretty good. Let's take a look what profit shows us. And for the profit, we have like a map of 7%, almost 8%. We have yearly seasonality, which is pretty interesting. So that the summer time, except for the July, so it's June and August, like in a pike, maybe this beginning and the end of the vacations. And yes, some highlight in January. Again, the trend. Let's move on. The QQ plot is a bit worse than for the SARIMA model, but still looking pretty good for some of the quantiles. So the residuals here are not normally distributed according to our tests. What about the XGBoost? Let's take a look at the XGBoost model. So we evaluate the model. Let's take a look at the MAP. Yeah, MAP is 13 or like 13.5%, and the QQ plot is not that good actually. So, but the residuals are normally distributed according to the statistical test. Let's have a summary table for us just to visualize, and we can see that the top champions are the SARIMA and the Prophet. But on the holdout data set, so just a test data set, let us use cross-validation to double check. Maybe we're just lucky, but we need to have a stable prediction. Just let us wait a little bit. It won't take long. We have the data. So what is interesting, let's take a look at the map. Surprisingly, the map for the Prophet is lower than the map for the SARIMA, so maybe there was not enough data for the SARIMA to utilize for the small amount of data. Let's build some graphs. So for this particular scheme, the Prophet seems to be a winner. However, on the pure holdout dataset, SARIMA model prevails, and those are graphs for MSE and MAE. Let's take a look at the map. Again, yeah. So with this in mind, as a recommendation, I would choose to double check the SARIMA model and Prophet model and maybe choose one of them. Because, yeah, this notebook demonstrates how to approach time series analysis with diverse modeling techniques, from classical statistical models like SARIMA to modern machine learning approaches like random forest, XGBoost, and specialized tools like Prophet. The key takeaway is the importance of evaluating models and use both metrics and residual diagnosis to ensure robust forecasting and real-world applications. And do not forget to use cross-validation. And feel free to modify the parameters, and this notebook will be shared with you, and apply these techniques to other datasets to gain insights. And thank you. Welcome back, and let us continue. Let us discuss some practical considerations in time series modeling. Before building any time series models, and proper preprocessing is crucial to ensure accuracy and reliability. And let us break down this process into three main steps: handling missing values, differencing, and transformations, and like scaling and normalizations. Handling missing values, there are a lot of approaches, and what differs some approaches from the classical ones, like from the ones in regression or in classification, is like forward fields and interpolation, because we should keep in mind that there is a temporal information also. So you should fill within some kind of window, or like use any sophisticated logic, since it's the time series and the order is important. And differencing helps remove trends in seasonality, and there are different ways how to difference the values. As for the transformations, well, log transform, square root, just to stabilize variance, and of course scaling and normalization, they are important for machine learning models, and like you can use techniques as min-max scaling and standardization. But also keep in mind that sometimes you'll need to apply those in the rolling window. Otherwise, you will scale the whole dataset, and that might not be the best solution. To give you some examples, well, transformations like log or square root are applied to stabilize variance and reduce the impact of outliers. For example, if your data shows high spikes, taking the log can compress those peaks and make the data more uniform. If we're talking about like scaling, so imagine that you're working with the stock prices that range from $10 to $10,000. Scaling ensures the model treats these differences fairly rather than just overweighting the larger values. And handling missing values, applying transformations like differentiating, scaling, and like all fundamental steps in preprocessing time series data, that are important. They help your model make more stable predictions. They help your model to be more stable. And these steps ensure the data is clean, consistent, and suitable for accurate modeling. And what about the feature engineering? So it is one of the most critical steps in time series analysis, and it helps the model better capture patterns and dependencies in the data. And let us explore three key techniques: lag features, rolling statistics, and time-based features. As for the lag features, they're created by using past values of the time series as predictors for the current value. This is based on the assumption that the past data points have an influence on the future values. For example, if you are forecasting sales, you might use the values from the day ago and 2 days ago, like also as an input features, and like they are mathematically represented just like this. What about the rolling statistics? It involves calculating metrics like moving average or moving standard deviation over a specific window of time. And these features help smooth out short-term fluctuations and highlight long-term trends or variability in the data. And like example is 7-day rolling average can give a smoother view of daily sales trends. Similarly, rolling standard deviation can be used to capture periods of high or low variability in the data. Of course, there are time-based features. Like imagine you need to encode the month, and if you apply the label encoding, the December will be like the 12th month, and the January will be like the one. And it is pretty bad if we're talking about time series, because those 2 months are close to each other. But if you use the label encoding, they're just super far away. Time-based features are derived from the temporal attributes of the data, such as the hour, day of the week, month, or quarter, and they're useful for capturing seasonality or recurrent patterns. And for cyclic features like months or hours, we can encode them using sine and cosine transformations to preserve the cyclical nature. And this avoids issues where December and January seem far apart numerically, but they actually like close to each other. These transformations are one of the ways. There are several options to do so. And just to summarize, so lag features help capture past dependencies, and rolling statistics highlights trends and variability. Time-based features, especially with cyclic encoding, allow the model to capture seasonality and recurrent patterns. And feature engineering ensures that the model has all the necessary context to make the accurate prediction, which is especially important in time series forecasting. But as I mentioned, we also need to keep in mind the data splitting. So the simplest approach is to train the model on past data and test on the future data. For example, if we have 10 years of data, we can train the model on the first 8 years and then use the last 2 years for testing. This ensures that the test set reflects future that the model has not seen. For better model evaluation, we can use time-based cross-validations, and there are two common strategies. The first one is rolling window, and the train set expands over time, including more past data as we move forward. For instance, if the first fold we might train on the first year and test on the second year. In the next fold, we train on the first 2 years and test on the third, and so on. So we extend. There is also a sliding window, and in this method, both the training set and test set move forward in time, maintaining a fixed size. This is useful when the system's behavior changes over time and we do not want older data to dominate the model training. These methods provide a more robust evaluation by testing the model on the multiple time periods. And please avoid common pitfalls. The biggest pitfall in time series splitting data is data leakage, where future information influences the training set. This happens a lot, and this can happen if, for example, rolling averages or future time points are included in the training set. Another common issue is failing to generalize the model to future data, which can result from non-testing on unseen time periods. Always ensure your test set contains data points from a future time period that the model has not seen during training. Take a look at the diagram. In the first row, the data set is split into one training and one test set, following a simple time-based split. And in the second, we extend the train set and move the test set, and we go sequentially. Just as a summary for this, always maintain temporal order when splitting time series datasets to prevent data leakage. Use simple time-based splits for straightforward evaluation and time-based cross-validation methods like rolling or sliding window for more robust model assessment. By applying these strategies, we ensure that our models are evaluated realistically and perform well on future and unseen data. Since we talked about this, how we evaluate, which metrics would we use? As for the metrics, it's straightforward. We can use metrics from regression, basically like mean absolute error, root mean squared error, mean squared error, like MAPE, mean absolute percentage error. Sometimes it is wise to split the test into the periods if you have big test, just to validate how your error increases over time. And also keep in mind that you should apply residual diagnosis, and you should check autocorrelation function, and you can check the normality of residuals by using QQ plot and tests like Shapiro. Residuals should be normally distributed. One more interesting metric is the statistical metrics for model selection. If you have several ARIMA models, you need to choose one. Well, you can use Akaike information criteria, and lower values indicate a better model. And typically it is used for selection of the models. You can use also the Bayesian information criteria, so it depends which one would you like to use. One more thing to mention, confidence intervals in time series. When forecasting with time series, it is important not only to provide a single prediction, but also to quantify the uncertainty around that prediction. This is where confidence intervals come in. A confidence interval gives us a range of values within which we expect the true value of the forecasted variable to lie, of course with a specified probability. For example, a 95 confidence interval means that 95% of the time the actual value is expected to fall within this range. And this range accounts for uncertainties in the data and the model. And in the graph, you can see the orange shaded region, and it represents the confidence interval around the forecast. And the center line is the predicted value, and the intervals provide a range of uncertainty, widening as we move further into the future. And the confidence intervals are important. They are sometimes critical for decision making because they provide a measure of uncertainty. They help you understand how much trust you can place in the forecast. For example, if the intervals are very wide, the precisions are less certain. In fields like finance or inventory management, knowing the range of possible outcomes helps organizations plan for the best and worst case scenarios. And of course, confidence intervals provide context to stakeholders, showing that forecasts are not exact but come with a range of possible values. How to estimate the confidence intervals? There are a lot of methods. We'll briefly take a look at a couple of them. Since we understand that confidence intervals are important, we'll begin with the classical time series models. Basically, the models have built-in mechanism like ARIMA and SARIMA, and they estimate those confidence intervals. They calculate the variance of residuals, the difference between actual values and predicted values, and use this variance to construct prediction intervals. For example, when forecasting with ARIMA, the model generates upper and lower bounds based on the variability in historical data, assuming a normal distribution of errors. And this allows us to capture the range of likely outcomes for future predictions. As for the tree-based models like random forest gradient boosting, while there are quantile regression forests, tree-based models can extend to quantile regression to estimate the specific quantiles, such as the 5th and the 95th percentiles. And this provides direct prediction intervals instead of just a point prediction. And it is useful when data distributions are non-normal or asymmetric. Bootstrapping is another method commonly used with the tree-based models, and we resample the training data with replacement and train multiple models, and then form the predictions of those models and create distribution and calculate percentiles to determine the confidence intervals. And the methods work well, when you don't have built-in intervals but want to capture the uncertainty in the predictions using statistics. As for the profit, well, it has a built-in prediction intervals. It includes variability in trends, seasonality, and other components to estimate prediction intervals. And by default, it provides 80% and 90%, 95% intervals, but these can be adjusted based on the application. And this makes, again, profit interesting model and useful for practical scenarios. And regardless of the methods used, there are a few best practices to keep in mind when estimating and interpreting confidence intervals. The first one is choose appropriate confidence levels. Select intervals that match the context of a problem. For instance, in financial risk assessment, 95% confidence might be appropriate, while 80% might not be enough. Assess interval width. Wider intervals indicates greater uncertainty in the model. If intervals are too wide, it might signal in a need to improve the model or to clean the data. A narrow interval suggests the model is confident, however, may risk underestimating variability. And of course, validate confidence intervals. Compare predicted intervals with actual outcomes to ensure that are well calibrated. For example, if you predict a 95% confidence interval, about 95% of the actual values should fall within that range. And just to sum up, different models provide various ways to estimate confidence intervals. And classical models rely on residuals variance, tree-based models use quantiles and bootstrapping, and Prophet simplifies the process with built-in intervals. But remember to validate and interpret the intervals carefully to make informed and meaningful decisions. And we're moving to the advanced topics and best practices. Dealing with seasonality and trends. There are advanced techniques like using complicated models and capturing complex seasonality. And you can use seasonal trend decomposition using STL, and decomposes time series into trend, seasonality, and residual components effectively. There are also exponential smoothing methods that captures trends and multiple seasonalities and nonlinear dependencies. And of course, like there are various ways to decompose time series. We can use differencing. We can use polynomial fitting just to model nonlinear trends. And we can use like other sophisticated approaches. And of course, we can model nonlinear trends using like nonlinear transformation, like a log transform or any other transformations, just to transform the data to be linear in another form. Another interesting topic, we won't cover it like fully today, we'll just mention, is the handling multivariate time series. A multivariate time series consists of multiple interdependent variables recorded over time, and unlike univariate time series, where we analyze and forecast a single variable, multivariate time series involve interactions between multiple variables. For example, economic indicators like GDP, unemployment rate, and inflation rate, where changes in one influence the other, and sensor reading from the IoT devices, where multiple sensors provide correlated measurements over time. Of course, there are challenges in those modeling, like increased complexity and high computational requirements. But there are models to solve these tasks, and yeah, that's pretty interesting task to solve actually. The next interesting task is, let me move a little bit. So yeah, is anomaly detection in time series. Anomaly detection in time series is crucial task that involves identifying unusual patterns or outliers in the data. And these anomalies can represent critical events or errors that require immediate attention. For example, in financial application, anomalies could indicate fraudulent transactions. And in system monitoring, they might signal hardware failures. And in manufacturing, anomalies can highlight quality control issues. And identifying such deviations early can help prevent larger problems and ensure smooth operations. You can use the simple statistics like z-score or modified z-score or moving average to highlight those values, or you can use more sophisticated approaches like machine learning approaches, like one-class SVMs, autoencoders, isolation forest, just to train a machine learning model that will take a look for the anomalies. As I mentioned during the talk about the prophet, is the change point detection. The change point detection identifies the moments in time series where the statistical properties such as mean, variance, or trend change significantly. And these points indicate shifts in the process which could have a real-world implications. For example, in financial market, a change point could indicate a trend reversal in stock prices. In climate data, it might signal a sudden shift in temperature patterns. There are various models, various statistical models to do this task, and you can use machine learning approaches, you can use like segmentation algorithms, and there are of course like domain specific approaches where you can use your domain knowledge. And this task is particularly interesting if you go into the production, since like this is part of the production monitoring system. Moving to the best practices, just to sum up, the first best practice is proper model validation. Time series data requires validation methods that respect its temporal structure. For example, instead of random cross-validation, you should use time-based cross-validation techniques like rolling or sliding windows. This ensures that the training data always precedes the test data, preventing data leakage. Additionally, it's important to validate the assumptions of the chosen model. For instance, ARIMA models assume stationarity, so you must test it before building the model. And if the assumptions are violated, the model may produce unreliable results. The second one is the importance of domain knowledge. Using domain knowledge is essential for effective time series modeling. Experts can provide insights into the data's processes, which can guide feature engineering and model selection. For example, a retail manager might explain the impact of seasonal promotions, helping you create better features for seasonality. And understanding the context behind the data is also helpful when you interpret the model predictions and when you make informed decisions. Models are tools, but domain expertise ensures the output are used meaningfully. And please monitor and update your models. Time series data is dynamic, and the patterns you model today might change in the future. Continuous monitoring is critical to track how well the model is performing over time. For example, if a sales forecasting model starts showing increased errors, it might indicate a shift in customer behavior or market conditions. And to maintain accuracy, you should periodically retrain models with the new data. And this ensures the models adapt to changes in the underlying patterns and remain relevant for future forecasting. And as for the documentation and reproducibility, keep detailed records of your work, and it is crucial for reproducibility and transparency. Document every step of the process from data preprocessing and feature engineering to model parameters and evaluation metrics, especially data validation and testing, how your model is tested, how the dataset is collected. This not only helps you or others to reproduce the result, but also ensures the analysis can be audited and improved in the future. Reproducibility is especially important in collaborative environments and industries with strict compliance requirements. Okay, let us have a key takeaways. So we discussed what a time series is. It's data collected over time and often shows patterns like trends, seasonality, random changes. And recognizing these patterns is important because it helps us choose the best tools for forecasting. Second, we looked at how time series is different from regular predictions. Time series models understand that past values can affect future ones, while regular prediction models assume each point is independent. This makes time series unique and requires specialized models. We talked about the models you can use. Traditional models like ARIMA and SARIMA work well for trend and repeating patterns. And for more complex data, tools like tree-based models, ensembles, and Prophet can be used, and they are useful actually for dataset with multiple time series. Advanced techniques can also be used to uncover hidden patterns. And we also covered how to prepare and work with time series data. Cleaning the data, fixing missing values, adjusting the trends, and scaling is essential. And adding features like lag values or average over time can make predictions better. And lastly, we discussed best practices. Always test your models properly to avoid errors or overfitting or data leakage. And use your understanding of the data's context to make better predictions, and do not forget to keep your models updated as the new data becomes available. And with these key takeaways in mind, you now have a solid foundation for working with time series. And thank you for your attention. I would like also to mention that I hope that this lecture has given you an understanding of how to approach time series analysis with confidence. We have covered the basics, but the time series topic is deeper. I highly recommend, if you're interested, take a separate course specifically on time series. And remember, forecasting is as much about understanding your data as it is about choosing the right tools. And as you move forward, I encourage you to experiment with the methods we've discussed and explore how they can be adapted to different datasets and challenges. Do not hesitate to review the concepts we covered. Learning and practice go hand in hand. Yeah, I'm here to support your journey, so feel free to reach out to me if you have any questions. And let us work together to deepen your understanding and apply the skills effectively. And thanks again, and I look forward to seeing your projects and insights. And have a great day.